in terms of readings, you should be done with chapter 1 and 2 in Macquarie. So these should be done, and you should really start working on reading chapter 3. Okay, it's the day of the pen's not working. Okay, so you should really read chapter 3. We'll start problem set 1, and I would, and you should know how to derive the canonical ensemble. So you should know conceptually how it works, and you should know of the sort of essential math in it. So this is something I really want you to go explicitly through. And the canonical ensemble in the classic derivation, the one we did last time, not the Chandler one. And I know many of you have been working on that because I've gotten some questions about that. But try to see if you can build it up from the start, so to make sure you all understand all the conceptual steps as well. So let me sort of remind you here what it is, right, without the explicit math. The basic idea by which we found the equilibrium distribution for a canonical ensemble is that we took a bunch of replicas of the canonical ensemble. So each of these systems was the canonical ensemble. And we took a bunch of replicates for which we embedded as a microcanonical ensemble. So the basic concept here is that the fluctuation in one of the canonical replicas is only a minor perturbation on the energy of the whole system, and that you can kind of push to infinite accuracy by going to the infinite limit. We then define the distribution, which was a set of occupancy numbers. You could think of them like that. A1 saying how many systems are in state 1, A2 saying how many systems are in, how many of the replicas are in state 2. And since the probability for each distribution, so the probability for a given distribution of energy is equally likely, and the probability for a given distribution would be equal to the multiplicity of this. So this would be proportional to the multiplicity of this. And so then what we did is we found the maximal for the multiplicity. So what we found is the distribution, A bar, that gave maximum W. So and that led us to the relation between the probability of a microstate and its energy, the probability being proportional to the exponential of minus beta d energy of the microstate. And if you think through this, and we're going to do a little more of that today, the reason that this appears in the Hamiltonian, the energy here, we call this the Hamiltonian, though it's not truly a Hamiltonian. The reason this appears in the exponential here is because this is the fluctuating quantity in the replicas, right? And therefore we had a Legendre multiplier which constrained the sum of all the replica energies to be equal to the microcanonical ensemble, and that's how that appeared. And so what that's already telling you is that if I have other things that fluctuate in here, like let's say I have a grand canonical ensemble where the amount of particles in each ensemble fluctuates, that will have to appear in here as well with some other Lagrange multiplier, right? So you can already start thinking what goes in the exponential for your probability, how in general it will look, right? It needs to contain the things that fluctuate in the ensemble with some kind of constant in front that weighs it. We then did fairly lengthy and painful math to show you, right, what beta is, that it is related, that it is 1 over kT. We started building some useful connections to thermodynamics, and that's something I want to continue today. So if I can summarize here. So this is one equation. We had the probability one. We also showed that the energy is the derivative or minus the derivative of the log of Q with respect to beta. And then through the Gibbs-Helmholtz relation, we found that the free energy is minus 1 over beta log Q. And so far, this is our basic equation for the canonical ensemble, and then we have the two relations with thermodynamics. And of course, since we have the free energy, we can in principle get every other property, right? Because in thermodynamics, everything is related as to the free energy by being a derivative or a second derivative. So, you know, if I took first derivatives, I would be able to get things like volume and pressure. I would be able to get entropy. If I take second derivatives, I would be able to get property information like heat capacity. So the general structure of how we develop statistical mechanics and its relation to thermodynamics. So if I put thermodynamics on one side and statistical mechanics on the other, so in thermodynamics, the key issue is the free energy function. And in a canonical ensemble, that's a function of NVT. In statistical mechanics, the key issue is the partition function, which is a function of NVT. And then the properties are derivatives of these, right? So and obviously, since these are simply related by taking a logarithm, if you can take the derivative of the free energy, you can take the derivative of the partition function or the log of the partition function. We will see a similarity like this for every single ensemble we do. So if I do a grand canonical ensemble, I'll have another potential, I'll have another partition function, but the structure of the derivative relations will be same if you write them in the proper units. So in principle, we already have an equation for entropy. We have the Boltzmann equation. But there's another equation that is often introduced for entropy, which is the Gibbs equation for entropy, which I just want to prove to you. They are both correct. They are essentially restatements of each other. So entropy in the Gibbs formula and the Gibbs formula for entropy states that the entropy is minus the Boltzmann constant. Again, that's just a unit issue, right? It's stating that the fundamental units of entropy are the Boltzmann constant or the gas constant. Sum over all the states, I'll label them I here, pi log pi. Let me quickly prove that to you, and then I'll do some useful things with that. So the proof, I'll take that equation. I'll start with what actually pi is. Pi is the exponential of minus beta ei over q. I'll take, I'm going to take the log on each side. So I'm going to take the log here and I'm going to sum over all the i's. So then I get on this side, I get sum I pi log pi. Sorry, I should have said I'm going to first multiply by pi We'll take the log and multiply by pi and sum that. So if I get that here, when I take the log, the exponential disappears. So I get minus beta sum I pi ei, right? That comes from this term here. I took the log, that dropped down. From that, I got minus beta ei, and then I multiply by pi and I sum. And then the other term simply gives me minus the log of qi. Because when I multiply that by pi and I sum over all the pi, that gives me 1, right? Okay. So what I have here now is that this is minus beta times the average energy minus the log of q. And the log of q, or minus the log of q, right, that is equal to beta times the free energy. So what I get here is this is beta times the free energy minus the average energy. And this here is minus Ts. So when I multiply by beta, beta is 1 over kT. So I've proven here that this is minus S over Kb. So I've just proven the Gibbs formula for entropy. And it's sometimes a little more practical than the Boltzmann one. Okay, let's first check it with Boltzmann. So let me do some interpretation, but also some checks on it. So if you apply this now in the microcanonical ensemble, so at constant energy, right, then the energy EI is a constant, which I'll just call E. So that means that all PI are constant, so all PI are the same, so all PI are equal to 1 over omega. And so when I sum I PI log PI minus KB, so when I get the log of PI, I get minus log omega. So this is KB sum I pi log omega, because I've canceled the minus sign here by taking the log of 1 over omega is minus the log of omega. So here I'm summing something that's constant, so it can actually go outside of the summation sign, and then I just sum over all the probabilities, so this is equal to KB log omega. So from the Gibbs formula, I've recovered the Boltzmann formula as it should, right? So that's good. The reason I really like the Gibbs formula is that it shows the true nature of entropy. So entropy is determined by the distribution over the microstate, right? It's a sum of probabilities over microstates. So it depends on the distribution itself. You're not actually averaging some microstate entropy here, right? So if you look at this thing here, right? If this were this log here were some like X, some extensive quantity in the microstate, then this looks like you're averaging that extensive quantity, right? Because you're summing over all the states times the probability of the states. But entropy is different, right? you're not averaging anything over the microstate. You're actually calculating a property of the distribution itself. So S is not a mechanical variable. There is no microscopic entropy that you average over. But S is a true property of the distribution. Of the distribution itself. You understand what I mean, right? Like if I write many of the extensive variables we average, right? If I had a volume fluctuating ensemble, then the average volume would be sum over all the microstates, probability of the microstates times the volume of that microstate. If I calculate the average energy, I sum I, Pi, energy in that microstate. And I can do that for all the mechanical variables. I could do that for magnetization. I could do that for polarization, but you cannot do that for entropy, right? And so entropy is our first, in some sense, true macroscopic variable. It is a property of the ensemble, not a property of the microstates. And that means, of course, that everything that contains entropy, like free energy, has the same issue, right? They are also properties of the ensemble. You can't say I have the free energy of my microstate. Entropy has a few other interesting properties, which, if you think hard about it, kind of have to fall out if they are a property of the distribution. But the first one I want to show you explicitly, that entropy is not influenced by the zero of energy. And this is trivial, but you want to remember it. It's actually often handy to solve problems. So let me say I have a set of energy levels, EI, and now I just want to substitute my reference energy, my axis. So I'm going to define a new energy scale. I'll call it EI prime, which is EI plus delta E. Right? So the delta E is a constant, right? I'm shifting all the energy levels in the same way. So what happens now to the probability? So let me calculate the probabilities with the shifted energy scale. So let me calculate Pi prime I. Okay, that's of course e to the minus b beta EI prime e to the minus beta EJ prime. Now I'm going to substitute in what actually this is. And so this is e to the minus beta delta E times e to the minus beta EI, right? That's this first term here. Sum over j, e to the minus beta delta E, e to the minus beta EJ. And since this is a constant, I can cancel this away. And of course, what I now find is that it's e to the minus beta ei over sum j e to the minus beta ej. And this, of course, is pi, right? It's the probabilities that would be defined from this energy scale. So I can shift the axis of energy without any change to the probabilities, and therefore without any change to the entropy. So things where that will help you, for example, is that, sometimes it's helpful in derivations to set the lowest energy equal to 0, or to whatever number you want it to be, and you will not be changing the entropy. So I've told you that entropy is a measure of how the system distributes itself across its microstates. So let's now talk a little bit about that distribution by first of all trying to understand the limits. So the limits of S with T. And of course, the easy ones to do are T going to 0 and T going to infinity, right? Okay, so let me first take T going to 0. T going to 0, that's equal to beta going to infinity, right? So what happens to the probabilities? So Pi is e to the minus beta ei divided by the sum j e to the minus beta ej. So what I'm now going to do is I'm going to order the energy states from low to high. So let's take lowest energy state. Is E naught, and then I order them, E naught is less than E1, less than E2, etc. I'm going to calculate the probability to be in the lowest energy state, right? So I'm called that E0. So the probability to be in the lowest energy state is e to the minus beta E naught divided by the partition function. But in the partition function, I'm going to factor out the ground state energy, just like I did before. So I'm going to put that up front. So that's e to the minus beta E naught times 1 plus sum over j will now go from 1 to infinity, right? So this is the sum over the ground state. This is now the sum over the higher order, the excited states, e to the minus beta ej minus E naught. Now let's look at that. Of course, this cancels, right? So what happens to this term here? Probably should give you a minute, right? What happens to these terms here as beta goes to infinity? These are by definition a positive quantity, right? Because E0 is the ground state energy, it's the lowest energy. So Ej minus E0 is positive. I'm multiplying by an infinity. So this is e to the minus infinity. So these terms all die, right? So I'm just left with the 1. So the probability is 1. So what have I proven? That if I'm at 0 temperature, then if the energy is equal to the ground state energy, which I'll refer to as E0 here, then Pi is equal to 1 if I'm not in the ground state energy, then Pi is equal to 0. Which you can also calculate from here, but of course, if you have a probability that's 1, then all the other ones have to be 0 because probabilities have to sum to 1. Okay? Let me know if you have any questions, okay? This is sort of fairly, I think of it as straightforward, but that could be because I've done it for 25 years, but it's sort of fairly fundamental, right? At 0 temperature, you're sinking into the ground state, essentially. You're constrained into the ground state. Your probability to be there is 1, which means you're there all the time. So what is the entropy in this case? Well, let's write the Gibbs formula, right? The entropy is minus Kb sum EI Pi log Pi, which if I write it out explicitly, first I'll write over the ground state, right? So that's 1 log 1, and then you have plus a bunch of 0 log zeros, right? So 1 log 1, that's equal to 0. What's 0 log 0? This is an important thing to know in this class from now on. Log 0 would be minus infinity, right? But any power is stronger than the log as it goes to 0. So 0 log 0 is 0. And if you don't believe me, what would you use to prove this? Some piece of math from like when you were 12 years old that's useful. You would use the L'Hopital's rule, right? Remember Hospital's rule, right? If you have a divergence, right, of limits, you would use L'Hopital's rule, right? Because you could write this as like, you can really write this as x log x, right? When x goes to 0. And that you can write as sort of x over 1 over log x. And that starts to look like 0 over 0. And remember, if you have limits that are 0 over 0, use L'Hopital's rule, right? So give it a shot. But it's something you want to remember. This happens a lot in thermo. We will often use the term x log x. And you have to understand the limits when x goes to 0 and when x goes to 1. And they're both 0. So the entropy is 0 in the ground state. So what have we really shown here? What statistical mechanics is telling us that when you go to 0 temperature, the system picks one state, the lowest energy one, and stays there. It does not fluctuate. As a result, its entropy is 0. This is highly reminiscent of the third law of thermodynamics, right? Where we said that the entropy of equilibrium states, blah, 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 went to 0 as you hit 0. And this is basically a proof of the third law. There's also another interpretation of this, right? I described to you in the beginning a microscopic system as, even when it's in thermodynamic equilibrium, as fluctuating between different microstates. That means that if you only observe the macroscopic state, you have a level of uncertainty about what the microscopic state is, right? Because the mapping of microscopic states to macroscopic state is many to 1. So if I just tell you the macroscopic state, there's a bunch of microscopic states that the thing fluctuates through. So if you want to know exactly what state your atoms are in at a given time, what position they have, what velocity they have. You have uncertainty. You actually don't know because they are distributed along a possible set of microstates. Except at 0 Kelvin. At 0 Kelvin, the entropy vanishes and therefore the uncertainty vanishes as well. There is no uncertainty in this distribution, P log P, because one P is 1, the other ones are 0. So one microstate now corresponds to one macrostate. So let's do the other limit as t goes to infinity, which is even easier. So when t goes to infinity, now beta goes to 0. So when beta goes to 0, then what happens to my probabilities? I have this set of probabilities, pi, which are proportional to the exponential of minus beta e nu. Oh, I wrote I, sorry. I. So if beta goes to 0, then all the energies get multiplied by 0, so they don't matter. So all the pi's become constant, right? So pi become constant. They're all the same, independent of the energy. And they're going to become, like in the microcanonical ensemble, they're going to become 1 over the number of states. So if you want to understand something about materials, it's sort of useful to keep a simple plot in mind where you plot the probability of microstates as a function of the energy. And so what I told you is when you have infinite temperature, then the probabilities are all the same. So this is t equals infinity. When temperature is small, then the probability sort of decays very fast. So this is t equals small. And of course, as t goes to 0, this becomes a delta function at the lowest energy. And then in between, in between these things just sort of, t medium, that's about the vaguest definition there is. You start to reach higher energy states, but with less probability than the lower energy states. So let's map that like onto a material. Let me give you an example of an alloy. An AB alloy. So let's say it's an ordered compound. So at low T, maybe it forms some sort of nice ordered structure, and that's its ground state. So I'm drawing this where, say, the dark balls are A and the white ones are B. So this is well ordered. In this case, the energy is low. If it lives in that state, the entropy is low. What happens as I raise the temperature? Well, what you know is as I raise the temperature, you will start to create some defects. Right? So some of these atoms may change position. So let's go like, intermediate temperature. So the energy is now, maybe call this E0, right? The ground state energy is now E0 plus, I don't know, n times E defect, if you have n defects. And the question is, what happens to the entropy? Is it higher than here or not? So Is the entropy higher here than here? Well, it has to be, right? So here it's, let's look at pi log pi. Here you're basically condensed into one microstate. Technically there are two, right? Because I can put the black ball here or here, but it actually doesn't really matter when you go to the thermodynamic limit. But if I say I make a state with one anti-side defect, the black goes here and the white goes there. So listen carefully to my words, right? My definition of the state, of the thermodynamic state, is it's a state with one anti-side defect. So one pair exchanged. You can do Gibbs or you can do Boltzmann, but why will it have higher entropy? I mean, what will omega be? You don't even have to get it exactly right, right? So when I say the state has one defect, that defect can be anywhere. I can take any pair of bonds here, right? And make it an anti-side. So the entropy is going to be KB log omega, and omega is going to be something like some constant times n, where n is the number of atoms here. Right, and A is going to be something like the number of bonds per atom, right? A is going to be a small integer. So I go to higher temperature. So, you know, normally this is the time of year in class where I say, you know, when you go home for Thanksgiving, how are you going to explain what you learned to your parents or grandparents? But I assume some of you might not be going home. So this might not be the right way to tell it, but if you had to explain a 6th grader, well, not a 6th grader, a 12th grader, why do you have defects at finite temperature? Because, you know, they have higher energy, right? The defect energy is positive. So why do you have defects at higher energy? Why does the frickin' system doesn't just stay in its low energy state? Let me give you a hint, and then you can answer. Is the probability of this perfect state, is it still higher than the probability of a state with a defect in a given position, like here? Right? I now want to compare the probability of two states. The probability of the perfect state or the probability of the interchange right there. Let's call the first one 1 and the second one 2. Which one has the highest probability? Come on, you can do this. Which one has the lowest energy? You know, it's very quiet in this room. I could use some sound. Otherwise, I should be playing music. Oh no, but then you hear the music.
They're the same energy or the same probability?
Say it a bit louder because, oh, I need to crank up my volume. Hold on. Say that again.
They're the same probability. I guess you said it first in the chat.
No, they're not the same probability. Because this one has lower energy, the perfect one. So it will always have higher probability. So if I take two states, right, let me just make clear again what I did. I take the state that's perfect, and I take the state where I switched, made a defect. The state that's perfect has higher probability than the state I switched. So why do I see defects?
If you count microstates, the perfect situation only has one perfect microstate, but the defects and on a macroscopic scale, if you can put in a defect on any one of, say, 10 to the 23 locations, even if the individual microstates are less likely than the perfect one, the sum of all those probabilities is greater than the microstate.
That's perfect. That's better than I could have said it. Because there's more of them, right? Because we have order n states here with a defect. So the probability that I see a defect is the sum of all those probabilities. And so this, remember, the state that I see macroscopically is the one with the highest number of realizations, the highest number of combined microscopic probabilities. And if I define my macroscopic state as having a defect, then I have order n of them. Whereas the perfect state, I have only one. So I will see perfection, no pun intended here, a lot less than a defect. Okay. In reality, it's a little more subtle, and I'm going to leave you with that, and we can talk about that in office hours or so. If I actually put this omega in this log, right, you'll see that I'll still have zero entropy in the thermodynamic limit. Because to take the entropy per atom, I'm going to have to divide the entropy by n, because this is the total entropy of the system. So it turns out that this omega is going to have some special behavior with n before you actually see it. But play a bit with that. Okay. I'm going way too slow. But this is otherwise way too much fun. Okay. Let me now do an interpretation of equilibrium. And this, I think, is cool. So if you're like warming up your breakfast burrito and so, now's the time to put it down. So what is equilibrium in statistical mechanics? So first, I'm going to give you the classic statement again, and then we'll do this in statistical mechanics. So let's say, classic thermo. I'm going to do a system under constant T and V, right? T and V constant. Well, and N. Sorry. I'm going to do T, V, N. So the way I would solve this, right, I would find the macroscopic state for which F, which is defined as U minus Ts, is minimal, right? Let's think what that actually means. I have a box that's at constant N and V, and outside there's some temperature field. So how can this box correspond with the environment? Well, it's at constant temperature. It cannot do work, right? Because volume is constant. So I can basically have heat going in and out, and that heat, that changes the average energy. So if you think about it, what is equilibrium? I'm asking, I can freely exchange heat here with the environment. I'm sort of asking at what level of energy is the system in equilibrium with the environment? So practically, this system will exchange energy with the environment till F is minimal. Now let's do the statistical mechanical equivalent. So I want to equilibrate the canonical ensemble. You know that in thermodynamics, I told you, always know what your system is, because otherwise you don't know what you're writing down, right? You don't know what the dVs and the du's are. The equivalent in statistical mechanics is always know what you're summing over. Sometimes you're summing over states, sometimes you're summing over distributions, sometimes you're summing over energies. So I'm going to do that today. So I want to ask about equilibrium in a canonical ensemble. So what I want to know is which average energy maximizes the probability. So which average energy is the most likely one that I will see? Because that average energy should be the one that you observe when you minimize the Gibbs free energy, if these two are consistent. Okay, so the way I'm going to do that, now rather than summing over states, I'm going to sum over energy. So I'm going to group states, microstates now with the same energy. And I'll say that they're omega E of them. So omega is the function that tells me how many there are at each energy. Okay. So then the probability that I observe a certain energy, it's the sum of all the states with that energy, right? So it is omega E times the probability that I hit that energy, which is minus beta E over the partition function. So this is the probability that some value of the energy occurs, right? So really this is just like a normal probability, except that I summed all the ones that have the same energy. And since they have the same probability, I can put them all together, and that appears in this omega term. So let me now see when this is maximal, right? So I want to know, when is this maximal? I'm going to do the same trick, that rather than maximizing this thing, I'm going to maximize the log of it. And since log is a positive function, I can do that. So I'm going to maximize the log of PE. And that's equal to the maximum over the maximum value of the energy over, okay, let's that blue is a separation line. Okay, so I get the log of omega. I get minus beta E, right? That's when I take the log of that. And then I get minus the log of Q. Q is a constant for a given ensemble. So I can just, it doesn't do anything to the maximization, right? So the only energy dependence sits in the omega and in beta. I need more colors. You guys okay with colors? I know it can be a little tricky to see, but it's so handy. But if there are colors you really detest, let me know. The pink is already gone. Okay, so I'm going to now multiply here by 1 over beta, so that this goes too. And by the way, I can do that because beta is a positive quantity, right? If I'm maximizing this, I can maximize that with multiplied by some positive number. But we have to do that to see the beauty, because what are we really maximizing? So I get 1 over beta here, so I'm maximizing kBt log omega E minus E. And this here, you know from Boltzmann, this is Ts. So what are we maximizing? We are maximizing Ts minus E, or that means I could minimize over E. I multiply by a negative sign, right? E minus Ts. So what I'm minimizing is the free energy, right? The Helmholtz free energy. Let's let that sink in for a second. To restate what we've actually proven. We've proven that the energy that in classical thermodynamics minimizes the Gibbs free energy, the Helmholtz free energy. As you can see here, the value of the energy that minimizes this term, which is the Helmholtz free energy, is the energy that has the maximal probability to occur. This is actually amazing, right? I just want to stress that for a second because it's sort of a mathematical statement of everything we've been saying and thinking. I hope you've been thinking it, is that this here, I would say, is intuition, right? The thing you see is the thing with the highest probability to be seen. So the energy we observe is the one with the highest probability to occur. That makes total sense when you think about it, right? You know, if I have 1,000 lizards and 999 are red and one is yellow, I will think lizards are, what did I say, red, whatever the most was, right? So the thing with the highest probability to occur is what minimizes the thermodynamic equations. It's the solution to equilibrium in thermodynamics. The reason this is so cool is because it shows that statistical mechanics and thermodynamics, even though they start from very different principles, are completely consistent. Just to pain you, I'm going to rewrite this one more time. So, what is equilibrium? Equilibrium is the maximization over E of kBt log omega E minus E. This you should hang over your bed because, I mean, think about it, it's beautiful, right? It's this shows this tug of war between I want to have low energy, right? Because if the energy is low, then minus E is large. But I also want to have high multiplicity. I want to have high omega. Right? This is a beautiful tug of war, right, in material science. I want to be low energy, right? Because then minus E is large. But I need to maximize not just this, I need to maximize this whole thing. So I also would like large omega. Because then I'm seen, right? I get out, I'm Paris Hilton. No, I'm not Paris Hilton, but and she's too old anyway. Anyway, I'm working myself in a hole here. And what is the thing that regulates that competition? It's T, right? Right? If T is large, this gets a lot of weight, right? If T is large, you care, you want to be seen. You care about multiplicity, right? You want to have likes. No. If T is low, you don't care about the omega, so you just care about the energy. And so think about it, right? This is all we know about materials that we intuitively so well known, right? If T is low, I expect the material to be in a low energy state. If T is high, I don't expect it to be in a low energy state. I expect it to be in a high entropy state. So this is why things are solid at low temperature, and things most of the time go to liquid where they have a lot more microstates, right? Because think about it, a liquid has removed the constraint from the solid, right? In the solid, you have to be in this nice periodic state, blah, blah, blah. In a liquid, you've removed that constraint, so there are a lot more microstates that obey your definition of macroscopic state. So omega is going to be a lot larger. So this is the one that has to hang above your bed. Okay. You know, this is the lecture of cool statements. Sorry, next time is not going to be so good. I have one more coming for you. It's the Wake Me Up Monday Morning lecture. If the previous statement was not good enough, wait for this one. The interpretation of heat and work. Okay, so again, let me remind you how this works in thermo. In thermo, the average energy, right, from the first law we know is TdS. There's a term that comes through the heat. And I'll just do volume work to keep our life simple, just minus PdV, right? So I can change the internal energy by a heat flow, and I can change it by a workflow, right? That was the whole idea why we talked about all these old historic people. Let's do this in StatMech. So in StatMech, the average energy is the sum over microstates, Pi, Ei. So I want to know how I change it. So I'm going to take the differential, and that's the differential of a bunch of products. So the average, the E average, is sum I Ei dPi plus sum I Pi dEi. Okay, up to here is just math, right? Okay, let's look at this first term. This is the one that causes a change to the energy. You're without changing the energy states, the energy of the states, but you're changing how you're distributing along them, right? You have a dP. You have a change in distribution. So this is the one that changes the entropy, right? Because the entropy, S is minus KB sum I Pi log Pi. So if I change the distribution, I'm changing the entropy. So this term here really should be very related, if not the same as this term, right? Because that's what this is telling you, right? I'm changing the average energy by changing the entropy. This is exactly what I'm doing here. I'm changing the average energy by changing the entropy. And so here I have the opposite. Here I'm keeping the distribution the same, but I'm changing the energy levels. So I'm doing this at constant entropy, right? Because the entropy is only determined by the PIs, but I'm changing the energy levels. So that's this term, right? So this here is heat. This is work. My work is done. Ha ha ha. No. So, I mean, remember the beauty of this, right? All these people in the 1700s and 1800s that were trying to figure out the difference between heat and work and blah, blah, blah. First figuring out that they both were units of energy. then later figuring out that they were kind of doing different things to a system, right? Which is why we needed the second law. Now you see what they're doing, right? Heat without work changes the distribution of your system across energy levels, right? If in most cases, if you pump in more heat, you just spread out over more energy levels because you pump in more energy. What work does, work without heat flow, right? So adding work to a system at constant entropy, does that remind you of anything like a differential in the exam? Adding energy at constant entropy through work. So if you add work at constant entropy, you're just changing the energy levels. So if you have a hard time imagining this, think of the particle in a box that we did, right? If I push on the box, remember that the energy levels depended on the length of the box. So if I do work on a box that contains particles in a box, right, then I'm changing their energy levels. If I do that at constant entropy, I'm not changing the occupation of the levels, okay? So this is kind of an important statement to interpret what heat and work are. And you now see that while they both add energy to a system, they do play a fundamentally different role here, right? And you can also sort of see why heat is much less useful. It just kind of creates more fluctuation, whereas work doesn't necessarily. Work just gets absorbed by changing bond energies and therefore energies of state. Okay. I think I said enough of that. Okay, so let's take a brief summary here. Let's do a summary of the thermodynamic connection. So far we've shown that for mechanical extensive quantities, the average is the sum over the ensemble probability times the quantity in the microstate. We calculated that the probability in a canonical ensemble is the exponential of minus beta EI over the partition function. The partition function is the sum over all states exponential. Notice that this is a sum of all positive numbers, right? Exponential is always positive. The relation between the partition function and the free energy is minus 1 over beta, the logarithm of Q. And notice that it has the right units, right? Because this is equal to kBt log Q. So you can also say this is minus kBt log Q. And the log has no units, so the units of energy come out of kBt. The internal energy, which is the average energy, is minus d log Q d beta. Also has the right units. And then you can write the entropy any way you want. A million ways to write entropy. S is minus kb sum I pi log pi. You know, if you ever forget how this looks like, it has to have a minus sign, right? Because logs of numbers that are less than 1 are negative, but the entropy has to be positive. So you need the minus sign there, right? The other thing is that a term like pi log pi has no units. So you need something to create units, and kb has the right units for entropy, right? So you can also write that in terms of the partition function. We haven't done that by writing the entropy as U minus F, so the internal energy minus F divided by T. And then if I add kb here and I add kb here, then I get that this is equal to kb times beta minus d log Q, that's the energy term, plus 1 over beta log Q. And Macquarie gives it pretty much in this form, but there's nothing particularly fundamental about this equation, right? It's really just writing the entropy as U minus the free energy divided by T. You got that? No, feel free to tell me if I need to go back to some board to for you to catch what's on it. So I want to very briefly start chapter 3 of Macquarie, which is on the grand canonical ensemble, which I'm not formally going to fully derive. I think I want you to know the spirit of it, the way I've sort of explained it before. But if you really want to read the whole derivation, it's essentially what we did for canonical. But in even more gory detail. And grand canonical has these brilliant initials, right? GC stands for grand canonical. Why would you ever need grand canonical ensembles? You know, there's plenty of times where things are open to the environment, right? So remember, grand canonical means T, V, and mu now. So there's only one extensive variable constraint of volume. But energy can go in and out, and particles go in and out. So grand canonical ensembles are often used, say, on surfaces. I know. Let's say you're into catalysis and you're looking at a platinum surface. Then maybe gas molecules come in and out of your system, and so you need to sort of equilibrate that with the environment. The one that I do a lot is batteries, where you have an anode, cathode, and they're separated by an electrolyte. I do a lot of lithium-ion batteries, so lithium plus can go in and out. And so if you wanted to study the equilibrium of a single electrode, not of the whole, but of a single electrode, that would be open with respect to, both lithium on one side and electrons on the other side. So it would be an open system. Again, things that are open with gas environments are the most common. Systems in which things diffuse in and out, very common, right? Okay, so what you would do here is you would write a characteristic potential. So your thermodynamic potential for an open system would look something like, you remember this, right? You would have some potential that's now has variables T, V, and mu, where mu is like the chemical potential of the particles that can exchange. So that would be defined as U minus Ts minus mu n. And the differential of that potential, so now you could kind of like totally blow out, like automatically it would be minus SDT minus PdV minus ND mu. And then you could calculate thermodynamic relations from this, right? Because you know that S is the first derivative of this with respect to that. P is the first derivative. Okay, let me do it. Right, minus S would be d phi dt at constant V and mu, and I'm already going to be out of space. Minus P would be d phi dV at constant T and mu. And I'm going to be smart and make space here. And N would be, minus N would be d phi d mu at constant V and T. Okay, why do I do this? Just to annoy you with more thermo. But no, really, that if we could find the partition function of the system, in statistical mechanics of a grand canonical system, we're also going to find that the potential is going to be the log of that partition function. It's again going to be -1 over beta, the log of that partition function. And I want to show you, if you had that potential, which now will show up as the log of a partition function, by taking derivatives, you can get all these other things. Okay? Just by looking at how the differential looks like. So now let's just spend a few minutes on figuring out how that partition function, or how the probability should look like in a grand canonical ensemble. You know, anything with grand in front is kind of grand. Like, you know, there's a Grand Hotel, Grandmaster Funk. It's pretty grand. I always loved the grand canonical ensemble. I don't know why, but it's slightly less boring than the canonical ensemble and has the word grand in it. Okay, how would you do the grand canonical ensemble? By now, I'm sure it's already on your pen, on your paper, right? Because you've totally know how to do this. How would you do a grand canonical ensemble? Okay, we would have my ensemble, a grand canonical ensemble, right? How would you get the probability distribution? Well, you would make replicas of it, right? And embed them, put them all together, and make a larger ensemble. And you would embed them, and the total would be a micro-canonical ensemble. Now the things that can fluctuate, or the things that can fluctuate here, is energy and number of particles. Right, that's what can fluctuate between these ensembles, but has to be constant for the total system, right? Because the total thing, this is microcanonical, so it's totally isolated from the environment. Okay, what are the constraints? Come on, each give me one so we can all go home earlier. Because I got to finish this in 8 minutes. What are the constraints? I wish I could give prizes. Well, I'm not getting any feedback. First constraint, right, would be that if I call these, okay, I'm going to define a distribution, right, which is again, number of systems in state 1, state 2, state 3, blah, 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 right? The number of constraints, let's call these AK. So K stands for this index. Okay, trivial constraints, sum over the number of replicas is some number A. Okay, I also need a constraint on the energy. So sum K, AK, the energy of the replica. This has to equal to the total energy. But now I have a third constraint, right? Because the particles can fluctuate in each ensemble, in each replica. So now I also sum K, AK, NK is equal to N total. Okay. I'm going to again find like maximal omega A bar, right? But now I have 3 constraints. So I have 3 Lagrange multipliers. So this one is going to give me alpha or alpha prime. This one is going to give me beta. And this one's going to give me gamma. Right? I truly hope that this looks reasonable to you, that you've studied the canonical ensemble well enough that you go like, yeah, of course, like. And if he let a 4th thing fluctuate, which Seder would really do on an exam, right? Seder would take a 4th thing that fluctuates, and then like I ask you what the 4th constraint is, right? And there would be a number 4 here, and there would be a delta multiplier. But if I asked you, how will the probability look like what will the form be of the probability of a microstate? Without messing around with the very lengthy and boring derivation to relate it to thermodynamics, you know how it's going to look like, right? The coefficient, the number of states that's in a given, the number of replicas that's in a given state is going to be proportional to e to the alpha prime or minus alpha prime, doesn't really matter, e to the minus beta times the energy, and e to the minus gamma times the number of particles. Right? This comes directly out of the constraints, right? Remember that. And the exponential, that comes out of the combinatorial form of this, right? This is what's going to give you the exponential, right? Because you do Stirling on the combinatorics, etc. So, you know, this is going to go away, right? This is going to be a normalizer because I have to normalize my probabilities to 1. So if you were to write down the probability of a microstate in a grand canonical ensemble, I think you can do that. I think it's going to look something like exponential. I just have to figure out where I put my beta. Minus beta energy minus mu nk. Oh, I'm messing up here. This should be nu. And then divided by, you know, summing this over all the states, right? This beast. This beast is called my partition function. It's called the grand canonical function. With a Greek letter theta. And this is where books and me and everybody else starts to diverge. You know, some books try very hard, just like they call every free energy thing different. There's H and there's F and there's G. Run out of letters, right? So same way, we're going to run out of letters for different partition functions for different ensembles. So we call the canonical one Q. The grand canonical, I think, is called theta in Macquarie. But after a while, Poisson infinity of boundary conditions. So there's an infinity of ensembles, and I run out of Greek letters, right? So at some point, I'm going to go like, I don't really care what the Greek letter is. Okay. If you worry a little bit about the details here, we'll do that next on Wednesday. You know, there's a bit of detail. Does the beta go here? Does the beta go there? We'll worry about that. Like, why is the beta in front of the two things? We'll worry about that on Wednesday. And it doesn't really matter. It just affects the definition of the chemical potential. So you can now, for the grand canonical ensemble, write down thermodynamic relations. And they're going to look remarkably like the other ones, right? So the average energy in the grand canonical ensemble is minus d log, I call it theta, d beta. The pressure is 1 over beta d log theta dV. And the reason is that the potential is minus 1 over beta log of the partition function. And so once you know this from the thermodynamic relations that I wrote up before, you get this, and then n is minus 1 over beta d log theta d mu. As you can imagine, there's sort of a system here that is starting to show up that, you know, somehow for most of these, the average of something is the derivative of the log of the partition function with respect to its conjugate, right? It's just that these conjugates are defined slightly different with respect to their relation to beta, but we'll come to that. That's exactly what we're going to do on Wednesday. But you can sort of see this a bit, right? P is a derivative with respect to V. Average number of particles is a derivative with respect to the chemical potential. It's just that because we work in the entropy notation, as I'll show you on Wednesday, the conjugate with energy is actually beta. And so if you think of them that way, again, if I'm totally confusing you, that's okay. This is just sort of like, you know, planting something in your neurons to be more receptive on Wednesday. So, but you'll see that this is totally normal. This is totally straightforward, the way this looks like. Okay, I'm done and tired. So enjoy the rest of your week. No, I'll see you on Wednesday. So enjoy the first few days of your week without me. So, and I'll see you next time. Bye.